In this video, we'll talk about introducing nonlinearities in simple linear regression models. Now, you might encounter many situations where the way we were introducing linear relationships between x and y may not be as accurate. And you might see that sometimes logs are used on data like wages, or data on wages or earnings or salaries, etc. And we'll see why. Okay, so let's take a look at the example we were running with before, which said that wage is a function of education, right? So this was hourly data that was observed, hourly wage data, and this coefficient right here was basically saying for each additional year of education, the return on that return is basically $1.43. Now, you might find this to be a bit strange because depending on where you are at, what your initial level of education is, if you add one more to that, it might have a different effect, right? Depending on whether you are at very low levels of education or very high levels of education, adding 1 year to your education should do much more than $1.43. Okay, so how do we incorporate that, right? So how do we incorporate the fact that we think that the additional years of schooling are worth a lot more in dollar terms than previous years, right? One way to do this is to introduce a constant percentage effect. So right now, what we have is just capturing a dollar effect, right? We're just saying that the hourly wage goes up by $1.43 with on average with each additional year of education, holding everything else constant. So if we wanted to capture a percentage effect, we could approximate percentage changes. We can approximate percentage changes using natural logs. Okay, so usually this is written as log or this. Okay. Or natural logs. Okay, so let's think about this equation where we have changed the dependent variable. So instead of having wage on the left hand side, we are working with log of wages, right? And so when we do that and we take the partial derivative, or basically when we hold u fixed, the error or the disturbance fixed, we get this expression, which tells us that beta 1 is basically the ratio of the changes in log wages with respect to the changes in education. And so we can use a result from calculus to interpret what beta 1 is here. What does beta 1 mean when we estimate it? Okay, so recall that, when you learned about logs, we basically said that there was a percentage change effect that logs can capture. So if you multiply 100 by the changes in the log of a variable, that's approximately equal to the percentage change in the variable itself, okay? And so when we write out an equation like this, we have a very nice clean interpretation of beta 1, okay? So basically, if we multiply 100, we multiply beta 1 with 100, we can say that this is equal to the percentage change in wages, okay, when the change in x is 1, okay. So let's take a closer look at what this means. So 100 times beta 1 is going to be called the return to education, because this is now free of units, right? We're just saying it's a return on our education. As education goes up by 1, there's some percentage change in wages, okay? And we're not talking about the units of wages. So no currency, no price level involved. This is cleaner. Okay, so here the graph is going to show the relationship between wages and education when u is equal to 0. So here you can see that this is sort of exponential, right? and this is not constant, like this doesn't have a constant slope, right? If we had a straight line that we fit through everything, then we would say that, well, the slope, right, as we add more and more years of education, as we go from lower levels of education to higher levels of education, right, there's a constant effect on wages if this was a straight line. But here we are finding that this is not a straight line, right? In the data, we find that this is actually, it has a curvature. The slope at this point is less than the slope at this point right here, right? So there might be a percentage effect that we should be able to capture. Okay, so here when we estimate the equation, you can also do this using wage 2 data. Okay, it's just called wage 2 in your package. Log of wage equals this, right? And so we want to basically interpret what this means, this coefficient means. Here we can say that the estimated return, the interpretation here is that the estimated return to each year of education is about 9.9%. Okay. And we also capture R squared here or here, it's the same, which is 16.5%. Okay. Now the R square from this equation and the equation where wages were not in logs are not comparable. So you don't want to confuse that, okay? Because we're trying to explain the variation in log wages here, but earlier we were explaining the variation in wages using education. Now, sometimes we might want to get elasticity, okay? And the way we measure elasticity is if we were to measure percentage changes, how percentage changes in X affect percentage changes in Y. So we might want to use logs on both sides of the equation, right? And remember that you cannot use log on non-zero. No, you always want to use logs on positive numbers, okay? So it's usually used for salary data, income data, etc. Okay, so here we have log of salary and we have log of sales. This is some other model that we are considering. So we might have sales revenues in dollars and we have salary in dollars, right? So these are positive and we can take this type of model and estimate it. So beta 1 would then capture the percentage change, what a percentage change in sales would do to a percentage change in salaries, right? And so here, elasticity is captured by beta 1, and this is free of units of salary and sales, okay, both X and Y. And the constant elasticity model for salary and sales makes more sense than a constant dollar effect. So if we had, for example, a log of salary and we were regressing that on sales, right? And this was in dollars, but this was, the coefficient here would capture a percentage effect. So this would basically mean here we would say that a $1 increase, a $1 increase in sales on average has, if this was, let's say, 0.09, then we would say a $1 increase in sales would increase salaries by 9% on average, right? And still this doesn't make any sense because one variable is in percentages, one variable is in dollars, so you might as well convert both in dollars.